Okay. Good afternoon, everybody. So today we'll continue discussing coherent states and how to utilize them to write down a path integral formalism for many-body quantum systems. So we are discussing today a system of bosons. And the bosons are described by some annihilation and creation operators that we use as building blocks to all our quantum states and operators to describe a many-body system. And they obey the bosonic commutator A dagger is delta of alpha alpha prime. Alphas are some quantum number of single particle, as usual. And now we want to be able to compute the following quantity. So we will focus only on thermodynamic systems, not dynamic. Of course, everything I do here with imaginary time can be done for real time, but real time is really much more complicated for many-body systems, so we will not deal with it in this course. But we are doing, sorry, better close the door. So we want to be able to compute a partition function, a thermodynamic partition function, that is quite generally defined as a trace over e to the minus beta h. Beta here is, throughout this class, will be the inverse of temperature, and H is Hamiltonian, describing the system using A and A dagger as the building blocks. So we started defining, so I want to remind you of the philosophy of constructing the path integral. We did it last week for a single particle, and we can do it in each problem for the appropriate basis of states. And we saw that the trick is to look at the time axis, or in this particular problem, which is a thermodynamic, it's the imaginary time axis of time evolution, imaginary time evolution, and slice it to tiny pieces where at each step the non-trivial commutators of operators become small enough that we can replace them by matrix elements, which are just C numbers. And in the end, we're going to get an expression which is no longer has explicitly any operator, only C numbers. And it's going to be a multidimensional integral. The price that we pay is that the integral is really multidimensional, or more precisely, it is infinitely dimensional. But if we think of multidimensional integrals as just the limit of a large number taken to infinity, we can, in practice, we can use it. We know how to calculate it exactly for particular cases, or make approximations. It all boils down to solving integrals. Okay, that's the advance. And besides, it has some intuitive flavor to it behind it, which supports this path integral description of quantum mechanics. But here, because our building blocks are these A's and A dagger, we want to use a basis of states which are eigenstates of these operators. Okay? Otherwise, we cannot do the prescription of the path integral, because remember, each time we want to introduce some matrix elements in the natural basis of whatever variables the Hamiltonian is written in. So we define coherent states as follows. So it is each coherent state is characterized by a complex variable phi that is not just one number, it is in fact a vector. Okay, so it's actually we can maybe write it like that. It's a set of complex numbers, phi alpha, where alpha are the same quantum numbers. And it is defined such that for every alpha, A alpha acting on phi brings out phi alpha times the same states. In other words, phi are eigenstates of A alpha with eigenvalues phi alpha. Okay? So this is a definition of a coherent state. And we would like to be able to write it in terms of Fock states. We realize that it's a state that is not a Fock state by its own, because a Fock state cannot be an eigenstate of an annihilation operator. By definition, it reduces the number of particles. But you can prove, and you are going to do it explicitly in your next homework, I think, that phi can be explicitly written as an exponent of the sum over alpha, phi alpha, A alpha dagger, all that acting on the vacuum. And we know that an exponential of an operator is just what you get if you expand it to an infinite series. So by definition, you can see that this is going to give you an infinite superposition of Fock states with different number of particles of each flavor. Okay, so you can just directly, by applying A alpha on this, you can prove that it's an eigenstate. And once we have it, notice that we can Hermitian conjugate the two sides of the equation and find that if you take phi, the Hermitian conjugate of the state phi and act with A alpha dagger to the left, you're going to get phi times phi alpha bar, where phi bar will denote a complex conjugate. Okay, so again, phi alpha are complex numbers. Okay, good. So this is one important step forward that we wish to keep in mind. Now, one can also show quite easily that we can, once we have this explicit definition of phi, it is easy to show that while phi is an eigenstate of the annihilation operator, it's of course not an eigenstate of. Yeah, you wanted to ask a question?
Yeah, and this is up to a normalization factor, right?
No, it is actually normalized. Yeah. It is sorry. No, we'll get to it. No, it's not normalized and it cannot be. Okay, we'll get to it. Sorry, thanks for asking, but it's going to be, yeah. I'm going to show it soon. So in fact, you cannot normalize. Of course, you can always multiply by something, but we want to keep it this way. So, so if you're acting with A alpha dagger on phi, of course phi is not an eigenstate of A alpha dagger, so don't get confused. This is just the Hermitian conjugate of this equation. But it is very easy to see that this is what you get if you take the explicit definition of phi and apply a derivative with respect to phi alpha, right? So it's going to be a derivative with respect to one of the variables, phi alpha, of acting on phi. And it's easy to see why you get it. You just get it's a derivative of an exponent and brings out the prefactor of phi alpha, which is A alpha times the same exponent. Okay? So, so this is interesting because if you look at these two equations, what happens to phi when you act with A alpha, it's giving you, it's just an eigenstate, gives you an eigenvalue, which is phi. A alpha dagger gives you the derivative with respect to the same phi alpha. What does it remind you of?
Positional momentum.
Yes, so that's right, except up to a factor of I, right? So, if you look at the state, let me remind you that if you act with, if you act with, the momentum operator is minus I VDX. So if you have states that are eigenstates of X, right? Something like this, then the P operator, when it acts on them, it acts like a derivative. And for that reason, if you want if you write the overlap between X and P, what it will look like, the overlap of a state with well-defined P and well-defined X, that's, we already used it last week. It's going to be up to normalization, something that looks like e to the I px, right? Okay, up to h bar. Okay? Right, actually I forgot the h bar here, but let's assume from now on that h bar is 1. Okay? Until the end of the course, I don't want to carry it on. Okay? Good. So this is this relation is intimately related to the expression that you get for this matrix element. And here we actually get something very similar because you see, in some sense, if you view A alpha as a sort of coordinate, then A alpha dagger is its momentum, conjugate momentum, or vice versa, doesn't matter. But it's missing the factor of I. So as a result, you can conclude that if you have the following overlap, it's between a phi and phi prime. Okay, so you take one coherent state and you consider its matrix element with some other coherent state, it's going to give you an exponential factor that looks like this. It's phi alpha prime bar, phi alpha. Okay? Now, and notice that it's reminiscent of this e to the IP, but without the I. Okay, so it's just a real exponent. Okay, this is a bit weird, but okay, we can deal with it. Actually, to get this, you can just take the definition and do the calculation. I think this you also will get in your homework. It's a simple exercise. And we're going to prove this identity. There is a closed expression for the matrix element relating phi to phi prime. Now, however, I want to notice something very funny, that if you are this is true for any phi and phi prime. Each of them are a set of numbers. In particular, as a special case, it's applicable to the case where phi prime equals phi. Okay, so let's see what it gives. So if you take phi to be equal to phi prime, it is just the inner product of phi with itself. It's going to give you e to the sum over alpha, phi alpha bar phi alpha, but phi alpha bar phi alpha is nothing but phi alpha absolute value square. Okay, so let me explicitly write it like this. That's what you get. And remember, phi alpha are some complex numbers, but their absolute value is a positive. That's a positive number, and what you therefore get is an exponential of a positive real number, which is larger than 1. Okay? Now, this is a bit of a problem if we want to talk about normalization, because we are used to a case, so usually the set of coherent states were a complete set of states or an orthonormal basis, and the phi overlap should give you, or phi prime should give you a delta of phi prime, and for the case that it's just the same phi, you should get 1, right? Or a constant number that you can divide by. But in fact, that's not what you get. You get something that is inherently bigger than, always bigger than 1, and in some cases, it can be even infinite, because the set of quantum number alpha can be an infinite, so it could be infinite. Okay, there's no limit to it. So, is this a problem? What does it actually show? And what is it implying? Is it implying that we cannot use the coherent set? So, in fact, we can use them, but we have to be careful. What this behavior implies is that the set of all possible coherent states is actually an overcomplete set. Okay? An overcomplete because it gives you a redundancy. It gives you, so if you want to write any other state as a superposition of coherent state, because it's overcomplete, you have somehow to normalize it in a careful way. And the way it will come in for our purposes, for the path integral, is if you want to write a resolution of identity. Remember, this was the key trick that we used. It was introducing resolution of identity, which projects to any complete set in the middle of any time step, and that's how we got our path integral. We're going to do the same thing, but we have to write the resolution of identity in such a way that it will indeed be an identity. And the way to do it carefully is that when you are integrating over all the possible phi's, you have to divide by this factor, and this will save us from this in fact will give us the correct description. So what I'm saying is that if I now take, so I'm now writing a resolution of identity. I want to write it here because we're going to use it a lot today. So this is what it's going to be. First, let me write a differential. I will define it in a minute. This is an integral over all the possible phi's, where each phi, I remind you, is in fact a set of complex numbers. It's not just one number, it's a set of complex numbers, maybe even an infinite set, there's no limit. And now, just like we always do, so usually resolution of identity in the case where you have just a regular complete basis looks like something like that, right? You take the sum over lambda of all the projectors. This is the standard. Now, instead, except the fact that we also have a multidimensional integral because they are continuous variables, you also need to multiply this projector by 1 over the overlap of phi with itself, which is not 1 or not normalizable, and in fact, it is just this exponential factor. Okay? So let us write it explicitly. I first want to define the differential. So this is a product over all alpha of d phi alpha bar divided by pi. Okay, that's the differential. Where is it coming from? It's coming from the fact that, maybe I'll write it here on the side. If you look at the integral, a complex integral, complex integral of e to the minus z bar wz, where w is just some number, let's say a real number. This is given by pi over w. Okay, where here z is just one complex variable, x plus iy, z bar is x minus iy, and you can see that if you convert z and z bar to, you make change of variables to x and y with the appropriate Jacobian, you just get a double Gaussian integral, a double real Gaussian integral, which usually gives you square root of pi over w, but because it's double, you get pi over w, okay? So in particular, if w is just 1, then you get pi. So if you divide it by pi, you divide the measure by pi, you get 1 from this. Okay? In other words, this differential defined in this way guarantees you that after you integrate over all the phi alphas, you're going to get 1. And this is indeed a Gaussian, because 1 over phi is e to the sum over phi alpha.
But here it's in a plus. Here it's in a plus sign.
Yes, but it's 1 over. It's
Okay.
1 over. Okay? That's the whole thing. You
Okay.
divide, you get divide by something that is bigger than 1. Therefore, it is normalizable in this sense, and because this, as I said, this exponent can be infinitely large if you have infinitely many variables in principle. So to be more explicit, we get a resolution of identity that is distance differential times e to the minus sum over alpha, phi alpha bar phi alpha, which is phi alpha absolute value square, to the minus sign. This is the Gauss, just the Gaussian. You see, so for each alpha, you get an independent Gaussian whose integral is just 1, and then you have the projector. Okay? Okay? Good? Great. So let me leave this in a frame, because we're going to use it quite often. Okay. Right, so now we are all set to do the path integral. So, with your permission, I will erase it. And let me just leave in here the definition. Because we're going to explicitly use that. Great. Okay. So now I want to calculate this partition function, and why this is what I want, because if I'm interested in the thermodynamics of the problem, the partition function gives you everything. Remember, any physical quantity is some derivative of it. It's like a generating function. And I want now to compute, in fact, not the canonical, but the grand canonical partition function, because for most of the many-body programs that we're interested in, the grand canonical ensemble is much easier, much more appropriate, because you don't necessarily have a well-defined number of particles, you have a chemical potential instead, okay? So I just remind you what is the grand canonical Hamiltonian. It's the Hamiltonian as the usual thing that we write as the sum of one body, two body, etc. terms minus mu, the chemical potential, times the number operation. And here, the Hamiltonian is something that we would like to write in normal order with the A and A daggers, and usually it has, to be most general, it has one body terms of the form, okay, A dagger A alpha prime. We can always choose a basis where this is diagonal if you want, but here I want to be completely general. Plus, I have some two-body term, which is a sum over 4 indices in general. Let me call them gamma and gamma prime. Some V, alpha, alpha prime, gamma, gamma prime. And here we have okay, right, and we can, in principle, we can also have three-body terms or higher, but all of them will be written in a normal order for convenience. Okay, and you're going to see that it's actually very useful for our purposes, because when you write an operator in its normal order, and the normal order simply means that you are subtracting its vacuum expectation value if it has one. And then all the annihilation operators are on the right and the creation on the left. And that will turn out very useful for our purposes. So that's the Hamiltonian. And N, the number operator, can also be written in second quantization as simply the sum over alpha. Okay, just sum over all the number operators. Okay, so now let's write the path into first the partition function from the definition. So the definition is a trace of the operator e to the minus beta h grand canonical, where a trace is a summation over some complete basis. It doesn't matter what basis it is, but formally, if it's a complete basis, not over complete, it's just the sum over alpha of, let me call it lambda, of lambda e to the minus beta h gc lambda. Okay, that's a definition of a trace. It's a sum over all the diagonal elements in some orthonormal basis. What would be the appropriate orthonormal basis for a many-body system of bosons? It would be, for example, Fock states. Okay? That's really a complete basis, an orthonormal basis. So these are the lambdas, and I don't need to write them explicitly. Just keep in mind that it's an orthonormal basis. Okay. Now I want to turn it into a path integral by introducing, so I usually calculating this matrix element is complicated, right? Who knows what, I mean, yeah. I mean, you can calculate it, but it's going to give you horrendous big expression, but what I know is that because it is nothing but some combination of A's and A figures, it's useful to compute, or it's relatively straightforward to write its matrix elements in a basis of coherent states. Okay, because what does it mean? In a basis of coherent states, any matrix element will just become an expression which is a function of the phi alphas and phi alpha bars. That's all. Okay, we'll see it in a minute. But before that, I have to introduce the coherent state. Right now, this is a Fox state or something else. So I'm taking advantage of the same trick we use all over the place. We introduce here the resolution of identity. Which one? This one? But with your permission, instead of the notation phi, I use psi. Okay? Just for getting a standard. Okay, so I'm introducing, here, the resolution of identity as integral d psi bar of e to the minus sum over alpha psi alpha square psi. Okay? Okay, and introduce it between the exponent and the left-hand side lambda. Okay? Okay, let's see what we get from it. Now I'm allowed to change the order. I have here a sum over lambda and the integral over psi. I can change the order, no problem. And when I change the order, I can also take out this exponential factor because it's nothing but a number, right? So I'm getting, let me write it in a convenient form, d psi bar e to the minus sum over alpha psi alpha absolute value square. And then I have my sum over lambda. I took out everything that does not depend on lambda and is not an operator. And what I'm left inside, what I still have inside the sum over lambda will still be this projector on psi. So I take this matrix element, original one, and I have d psi e to the minus beta h, ending with lambda. Okay? Good? Okay, great. Now I can easily actually eliminate the lambda completely in favor of the psi. Why? Because notice that now inside the sum of lambda, I have matrix elements. These are numbers, just complex numbers, each of them, right? And numbers I can reshuffle, right? So I can take this matrix element, it's some complex number, and reshuffle it here. It is allowed, right? Then I'm going to get this lambda, this whole thing will shift. Let me rewrite it as psi bar e to the minus sum over alpha psi here. And now in the sum over lambda, I will have psi e to the minus beta h gc sandwiched with lambda, and then lambda. Okay? Great. And now notice the following magic. I just look at this combination. Okay? This is the resolution of identity. Right? So I can eliminate it. It's just one. So well, actually, it is more careful. It is this. Okay, so what did I get? After eliminating this resolution of identity, I get that z equals just an integral over the differential psi bar of e to the minus sum over alpha psi alpha square times the matrix element psi e to the minus beta h psi. Okay? Okay, so the advantage of this is that I'm now going to I'm going to take this matrix element and compute it or bring it to a form that we can deal with by playing the same game that we played for the path integral of a single particle, which is to divide the imaginary time axis to small slices, neglect the commutator at each step, and replace this by a product of many matrix elements. But all these matrix elements will be in the basis of coherent states. And I'm claiming that this we know how to calculate from the definition. Okay, so let's see what it is. I'll erase all this. All right, so again, I remind you that the coherent states are such that any A alpha acting on them gives you just its eigenvalue. These are eigenstates, and similarly, if we apply a dagger on the left, we get phi alpha bar. Right? So therefore, if I have a general operator that is written in normal order, what does it mean? It's some combination of some product of A's to the right, some product of A daggers on the left, and it doesn't matter if this operator is Hermitian or not, it doesn't matter. Whatever it is, I know how to compute its matrix element between the state, let me call it, let me call it psi, doesn't matter, but some psi and some psi bar, psi prime, sorry, psi prime, not bar. Okay, so these are just two distinct coherent states. Each of them is a set of complex numbers, psi alpha and psi prime alpha bar. Okay? Now, what it gives you? So since O is normal order, okay, what it means by normal ordering is that it's some product of A alphas and some product of some other alphas of A alpha dagger, right? Okay, that's what it means. So all the A's acting on psi, what they give you? Just the same expression. It is all the same expression of psi alphas. Okay, every A alpha is replaced by its eigenvalue. And similarly, all the A daggers acting on the left will give you will be replaced by psi alpha prime bar. Okay, because this is the Hermitian conjugate. As a result, what I'm going to get is psi prime times the following C number. What I'm writing now is now a C number. It's it's the expression that I get if I take the expression of O in terms of A and A dagger and replace them by the complex number, namely it's some alpha prime bar, okay, with some set of alpha primes, psi alpha prime bar, and psi alpha, okay, where all the psi's are on the right or all the psi bars on the left, but it doesn't matter because now they are complex numbers, okay? And then this I sandwich between psi and psi prime, but the whole expression in the middle is now a number, a C number, okay? Or explicitly, it is just a product of psi bar alphas and psi prime bar alphas, because it's a different psi, and psi alphas.
It's some functional of psi, right? It's some functional of psi.
Exactly. It's a functional of psi and psi prime, right? Because it's a matrix element. So because it's a C number, I can take it outside of the matrix element, okay? And what I get is this functional, exactly right, whatever it is, but I still have the non-trivial matrix element psi and psi prime, which is not a delta, or it's not normalizable, but we exactly know what it is, right? We know already what it is. It is nothing but this exponent e to the sum over alpha of psi prime bar alpha psi alpha. So what I'm getting is, let me write the final result. We're getting that, with your permission, I'm just copying this and copy it. Okay, let me just quickly write back the number operator because we need it. So this is giving us e to the sum over psi alpha prime bar psi alpha times O of psi prime bar and psi. Okay? All right. Very good. Let's remember this formula, and now we're going to apply it for our matrix element that we have here. So what I'm doing, this I can do this. So what I have here, I have to compute a matrix element of the operator e to the minus beta h gc between some psi and some other psi, but it's the same psi outside. But what I can do now is to repeat the trick, which is to replace e to the minus beta h by a product over n capital N divisions of the time axis to small slices. Okay, so I have my imaginary time axis tau between 0 and beta, and I divide it to infinitesimal slices d tau, where d tau is beta over n. N is the number of time steps. We are now going to replace e to the minus beta h gc by a product over n capital N time steps, where at each time steps we have e to the minus d tau times h gc, and now what I'm going to do, and I put this product inside of the matrix element. And what I'm going to do next is, in between each of the time steps, I introduce the resolution of identity. Okay, so in other words, this is e to the minus d tau hgc once, then I have product of many terms. Now in the jth place, I have e to the minus d tau hgc, okay, this is jth step, okay, and this until I have the, so e to the minus d tau hgc. This is the j. This is j equal 1, and this is j equal capital N. Okay. Actually, let me start from the right to left, but it doesn't really. Okay, just for good measure, that we go from right to left. J is increased each time by 1. Okay. And now what I'm doing here is the following. In between each step, I put a resolution of identity. Okay? And now let's write down which resolution of identity we have. So in each step, I'm introducing a coherent state that I label with the index j. Okay? But each time I increase j by 1. So if I'm looking at some time step j, this would be j plus 1. Okay? Somewhere in the middle. Then here I will introduce a coherent state, a resolution of identity in terms of a coherent state that I label as psi j, and here with psi j plus 1. Okay, let me write it down explicitly. So this one is integral d psi j bar e to the minus, let me write it, okay, actually, I want to be a little more careful, so it's sum over alpha psi j alpha square, and then psi j, okay? And this resolution of identity to the left of the operator, I write as basically the same thing, but now it is a different coherent state. Psi j plus 1. Okay, and again it has the same form. And then we have psi, sorry, we ran out of space. Psi j plus 1, psi j plus 1. Okay? Good? All right, so I do this, and notice what I get in the j step. I'm going to get the following result. So at each j step, I sandwich this exponential between psi j and psi j plus 1. Okay, these states will already belong to the next step. Okay, so I'm just looking at what you have in the middle. So I sandwich the exponential between psi j and psi j plus 1. And I gain another integral, actually two integrals, okay? Or if you like, let us, because this is the j step, let's just keep in mind this integral over j of psi j, and I get here an exponential e to the minus psi j squared, okay? And at each j step, this is what I get. Okay, so let me maybe clarify what I keep for the j step, and then the j plus 1 step will have the same thing with j plus 1 and j plus 2, etc. So what I'm keeping, and I call it the j step, is this exponent sandwiched with between the j and the psi j and psi j plus 1, then integrating over the psi j and keeping this exponent. Okay, everything else will belong to the next one. Is that clear? Okay, I hope you write it down for yourself quietly. You'll see that I keep track of, I'm not losing anything. Let me write down what we get in the end of the process. What I'm going to get is an integral over a product of integrals over all the j's running from 1 to n of such time steps, okay? And each time step give me inside the integral some number, okay? Which depends at each step on psi j, but also on the psi j plus 1 via this matrix element. Okay, so let me write down what you get. I no longer need this. Okay, so this is what we get. Z is equal to an integral over product of j going from 1 to n d psi j bar. But notice that inside z, inside the expression that I already erased, there was another element that in the end, maybe I'll just quickly write it again. There was another integral over some psi bar, but and the exponent, etc. But here we have to close this. We have to close it with the same psi. Okay. Now, one of the psi, actually, let's say psi n is going to be identified with this psi. So we are already accounting for it. But the psi 0 will be identified with psi n. Okay, so there is a constraint on this. I can define a psi n equals psi 0. Sorry, it's not. To write it as an index. Psi n equals psi 0. Okay? So there are only n terms in the product, not n plus 1. Okay, the 0 and the n are the same. Okay, so that's what I'm integrating. Now what do I get inside the integral in each case? I have an exponential of what I had before, which is okay, let me write it like this, a minus psi use a shortcut notation. Okay, well, what do I mean by this? So each of the psi j's is itself a vector of many complex numbers psi j alpha. Okay, and this is just a scalar product, which you can explicitly write as the sum over alpha of psi j alpha squared. Okay, so let's write it somewhere here. Write it here. It's a definition, if you like. Just for shortcut of notation. All right. Okay. So this is just a scalar product, written without all the indices. This is what I have here. And now what is it multiplied by? It's just a matrix element between psi j plus 1 e to the minus d tau h dc and psi j. Okay? All right. Actually, if you want to be a little accurate, maybe it's better to write it as j going from 0 to n minus 1, so that it's well defined for each j. Okay? All right. So we are nearly there because we know how to calculate this matrix element. In fact, we have a general formula. Let's apply it. So what is this? Let me just write it down. This is, I'm just applying the formula, and I use the definition of the, actually, we can even write something more general here, which is psi j prime bar. Psi j is sum over alpha psi j prime bar. Psi j alpha. Okay. So, what is this? It's e to the plus psi j plus 1 bar psi j, right? Times the operator, which in our case is just e to the minus d tau times h. But now, instead of an operator, it is replaced by a C number, and the C number is the expression for the Hamiltonian with all the A daggers replaced by psi bar j plus 1. Like this. Psi of j, right? This is what I do. Well, each, again, psi j is a set of numbers, psi j alphas. Okay? Psi j is psi j alpha 1, psi j alpha 2 is itself a vector. Okay? So this is a C number now. Okay, it's just functional of many variables. This is it. Now let's collect all the terms together. So what do I have inside my integral? I have an exponential of the Hamiltonian, and I have a product of one positive and one negative exponent, and I can combine them together. Now everything is a number, okay? Not only that, because it's these all the variables are now numbers and not operators, I can replace a product by a sum, right? And instead of writing a product of many j's, I can write a sum over j of all the contributions from all the j's. Okay?
You mean sum on the exponent?
Yeah, inside the exponent, yeah. A product of exponents is replaced by an exponent of a sum. Okay? Right, so then I'm getting the following result. I'll define this shortly. This is capital D now. Okay. And I have here also a constraint that psi n equals psi 0. I'll define this in a minute, but what do I have in the exponent? I have exponent of a sum over j of put in curly brackets what I have. So first of all, I have a term coming from the product of these two exponents. In both of them I have psi j, but it's multiplied by psi j bar j plus 1 minus psi j bar. Okay, so altogether it is psi j plus 1 bar minus psi j bar multiplied by psi j minus d tau of h of some functional of psi j plus 1 bar and psi j. That's what I have in the exponent, and I think you easily recognize that what I have here is it's a derivative, namely if I now do the same trick we're doing many times, we multiply and divide by d tau, which is always allowed. Then this becomes a time derivative, okay, or more precisely, a derivative with respect to the imaginary time tau. In the limit, of course, the d tau goes to 0, which is where we're heading.
You need to define the capital Z.
The what?
You haven't defined
I have to define, thank you. Yes, let me define it. So let me define it here. D psi bar is now the limit. Notice this whole expression, eventually we're going to take the limit that n goes to infinity or d tau goes to 0. The limit of what? Of a product of j going from 0 to n minus 1 and the product over all alphas of actually let me just, this I already defined, right? So, which is itself a product of d psi j alpha with a factor of 1 over pi. Okay? So that's a definition of the capital D. And explicitly what it is, it's we have a big vector of complex numbers with two indices, j and alpha. Alpha is some quantum number. J is a time step that we are going to go to the limit that these time steps are infinitesimally separated, so we get a continuum. Okay? So, so we are almost there. We're almost in a position to get a continuum limit because, erase this. So we're getting that partition function equals integral psi n equal psi 0 as a constraint, capital D of, what do we have here in the sum? Let me just check that we have the signs correct. Somewhere. Somewhere I got the wrong sign.
It's the same as it is in the book. So
What?
it's the same in the book, so probably you're right.
Yeah. Okay. All right. Okay. I hope that's. Okay. So, what do I'm left with? So this thing in the limit that the tau goes to 0 is just going to be replaced by a time derivative. And this whole thing is multiplied by d tau, right? So this the same d tau that appears here. So I can take outside of the sum, I can take out a factor of minus d tau, right? Okay, so what I get is, let me write it like this, it's minus the sum over j of d tau. I take it outside of the parentheses because it's a common factor to these two terms after I turn this into a derivative. And now what I have is d tau, sorry, okay, now I see where the problem is. So,
Yes, you do integration of parts and then.
what I want to actually to trade, okay, so the way it appears here, this is fine, okay? So this is a plus sign, which I turn into minus minus, okay? And then it's going to be a time derivative of psi bar times psi j minus plus h, which is some functional of psi j plus 1 bar and psi j. Okay? Okay? Yes?
It's going a bit backward, but what do you mean when you write psi j? J is just,
So
you
J-
divided the...
So I have a sequence of different coherent states. Psi j plus 1, each of them is different set of numbers. Okay?
Okay,
But eventually I'm going to take the continuum limit. Okay, so that will be my next step. I'm going to change psi j into psi of tau, a continuous function of the imaginary time axis.
But psi is just a coherent state of a
Yes,
an
psi
idea.
is the number psi. What I write here as psi is in fact just this. That's what it is.
So it's got nothing to do with tau or beta.
No.
How can you...
Tau is not yet there. Okay, tau will be the continuum limit of this j. Okay, so what I did is the following. The first of all, I had just a factor of beta.
Okay.
But the factor of beta I can write as a product of capital N times e to the minus d tau. If I remember that each d tau is just, I imagine that it is a time step on an imaginary time axis. Okay? Now what I did, let's go back to the state where we still had operators. I introduced a resolution of identity, and in each time step, imaginary time step, I artificially introduced a variable psi j. Okay? not only one variable. In between each e to the minus b tau, this is exactly what we did last week with q and p. It's exactly the same thing.
But both psi j and let's say psi j plus 1 are coherent states.
Yes,
of
each of them define coherent states, because I wrote a resolution of identity in terms. This is where I started from. These coherent states I used in my resolution of identity.
And you for sure have an infinite number of coherent states?
Yes.
Okay.
Yes. No problem. I mean, again, it's just you define it so. And anyway, it's a variable that eventually you're integrating over. You're integrating over all of them, all the possible complex values. Okay, it's an infinite dimensional infinite integral. Okay, that's what we're going to get in the end. All right, so good. So let's try to quickly wrap it up. What I get here, so now I'm going to do the continuum limit. Up till now, the only place where I use the continuum limit is replacing the difference by a derivative. And you see that by writing a derivative, I already changed variable into a continuum variable. So what do I do? Let's erase this. I'm now doing, I turn the index j into a continuous variable tau that changes between 0 and beta. That's this axis, okay, because I took the d tau to 0. This is when d tau goes to 0. And psi j is a discrete index, is now going to be replaced by a continuous function of psi, of tau, where when I'm writing psi of tau, I still have to remember that psi is not a single number, it's an array or a vector of psi alphas. Okay, so psi alpha, psi of tau is, let me write it explicitly, is in fact an array, psi alpha 2, okay, that's what it is. And by the way, the alphas can, for example, be just a real space indices R, and then I'm going to replace this discrete array by functions of, complex functions of R and tau, space and tau. Okay? It's a possibility, maybe not a convenient one, but one that you can write in a well-defined manner. And then the last thing is that we're changing the sum over j d tau is going to be replaced by an integral over d tau between 0 and beta. Okay? Okay. Now there is one subtle step, that's what confused me with the minus sign. Here I have the derivatives is on the psi bar. And I forgot another thing. In the limit that j is a continuum, and j plus 1 are very close, if I have a local function, a local in time, okay, depends on some others, but I can actually replace, I can basically replace the psi bar j plus 1 by psi bar j. Okay, so that's a continuum approximation. And therefore, this is just going to be a local expression which depends on the field psi tau. Okay? Okay, so let's see what we get for the partition function. In the end, we get an integral over, this is the big capital D differential. It has a constraint. And the constraint now, the condition that psi 0 equals psi capital N turns into periodic boundary conditions on the tau axis. So in fact the tau axis is, okay, this is the tau axis in fact wraps on itself, and it's a circle where the point 0 and beta are identical. It's periodic boundary conditions. So we can write it as psi of 0 equals psi of beta. Okay. Okay, the field psi tau has periodic boundary conditions. That's what it means. And then what do we have in the integral? We have integral exponent of minus integral d tau from 0 to beta. And what do we have inside the integral? So now we have to be careful. Notice that here I have minus the differential of acting on psi bar times psi. But I don't like this minus sign. I do integration by parts. And then the minus, then it changes into psi bar times derivative over psi, right? And when I do integrate, why do I, can I do this integration by parts? What am I losing? Because then I also have here, when I do integration by parts, let me just do it quickly, then I'm replacing this by d tau of the whole thing, right? Plus psi bar d tau. But why can I neglect it? Because it's a first derivative over tau, and then I integrate over tau. So what I get is just the boundary term, and that's 0 by definition, right? Because it's periodic boundary condition. So altogether, what I get is, inside this integral, I have psi bar d tau psi plus h of psi bar psi, and when I say psi, I mean psi of tau. Okay, everything here is tau dependent. Okay? That's it. What is the expression that I have in the
action?
This is the action. That's an action. So the action, this I will just define as an action. Okay, and that's its form. Okay, it's an integral d tau. It's again a Euclidean action because it's imaginary time, but it has a very simple form. Plus h of psi bar psi, whatever it is. What I mean by h psi of is that, for example, if this is my h, then I take this expression and every a dagger I replace by psi bar, and every a I replace by psi. That's all. Okay, so I can write down h of psi. Actually, it's h grand canonical. Right, it also includes the minus mu n. Okay, I was a bit uncareful here. Here. So what is this? It's just, if I just copy the general expression, it's a sum over alpha alpha prime, epsilon alpha alpha prime, psi bar alpha psi alpha prime plus okay, the two-body thing, which is the same thing. I'm not even writing it, but you can easily do the conversion. And minus mu sum over alpha of psi alpha bar psi alpha, where every time I write a psi, it's a psi, it's local in time. Okay, this is all tau tau, the same tau. Okay. Okay, so what I got is in fact a field theory. Okay, so actually I'm integrating, it's a functional integral over an action e to the minus s. This is in units for h bar equals 1, remember? So otherwise it should be minus s over h bar. But h bar is 1, and that's the action, and we have an explicit expression for it. And I think, okay, I think this is almost the place to stop. We will continue next week. We are going to see how we, in some cases, we can actually compute it exactly. And if we cannot compute it exactly, we can do perturbation theory or some tricks, but we can use it to do calculations. And the advantage is that we got rid of operators and converted the problem into writing integrals. Okay? So one last thing that I want to comment, I will not do the details yet, is that here I wrote everything in terms of this psi of tau, which is a continuous function of tau, but it obeys periodic boundary condition on this tau axis. Therefore, this function of tau is a periodic function. And because it's a periodic function, it has a natural period. It is sometimes useful, in fact, it is very useful to replace it by its Fourier series. Okay, it's going to be really a Fourier series, not a Fourier transform. What is the natural period? The period here in the imaginary time is beta, which has units of time for h bar equal 1. Okay, because otherwise actually it should have been h bar beta. Okay, h bar equal 1. So the period, if the period is beta, there is an elementary frequency that is 2 pi over beta, right? So we're going to introduce a series of Fourier components with frequencies omega n given by 2 pi over beta times n, where n here is an integer. Okay? So there's a sequence of frequencies. Actually, because beta is an inverse temperature, omega is just 2 pi times T, the temperature. This is temperature, not time. Don't be confused. Times an integer. Okay? This is called the Matsubara frequency. And we'll do it next week. I'm going to replace psi of tau at each point in our action. I'm going to replace by its Fourier series. And why is it useful? Because if you look at the first term, it has a time derivative, right? So the Fourier series will replace it by a number by a factor of omega n, or I omega n. Okay, we'll do it next week explicitly, but that's basically, it's going to allow us to write the expression for the action as a summation over some indices of some functional offset. Okay, so we'll continue next week. Okay? And Sarah is going to do the tutorial at 6.
Let's start. Today's lesson will be about path integrals. Let's start with why we even think about it. What's the idea? Let's say we have some sort of particle, start at some point I, let's make it clear, I, and ends, finishes at some point F in space, right? In these 2 points, the particle location is deterministic, and it's an actual real point. But along the way, the particle doesn't just go in a straight line to the next point. It has some sort. It moves in a sort of a wave function. Its path propagates throughout space in a probabilistic manner, and it evolves in time until it reaches the end point. So, while in each point in time the particle is a single localized location, the movement of particle are delocalized wave functions. So let's suggest an experiment that you all know very well. The 2-slit experiment. Right. We call the top slit A and the bottom slit B. And I'd like to say that, let's say this is the z-axis. Yeah, this time, this one will be z, right? I want to find the probability to move from zi, the initial state, to zf. Right? Let's denote the initial location, the initial state, with the wave function I, and the final one, function f. And we are interested in the probability pi to f, which is equal to absolute value squared I. Now, let's look specifically. Sorry, I wrote them the wrong way around. It's I and F. I wrote them again the wrong way around. I and F. We read this from right to left. Okay. Now let's look at this operator, this function right here. And reading from right to left, it's over here, I, this actually has 2 different possibilities in it. First of all, we can start with in the location I, move to A, and then go to F. So I, A, F, or we can do the other way around. Go for B, and then go to F. F, B, basically I opened just my the equation that says I start in location 1 and end in location 2, and open it with the path. I start in location 1, then I can go to A or B, and after that, I go to F. Now, let's see what this do for our probability function. Be equal to this term squared, epsilon value squared, plus this term, epsilon value squared, plus this term times the conjugate of the second term, plus f a plus this term conjugated, the a term, plus times the b term, a I conjugated times okay. Well, the first two terms are just the probability of each path on its own, and then we have an addition to terms right here, which are interference terms. They mix the path of A and the path of B together. Even though those two paths don't interact, and when a particle goes through A, it can't also go through B, the probability of him going into either slit can interfere with one another. And this is what we see in the classical two-slit experiment, when we have the interference pattern on the output of the two slits. Now, now let's expand this model a little bit, and then we'll see how we solve this. Okay. So I want to go from two slits to the entire space. So let's do it by steps. First of all, the very easiest step is just to add more slits into my like wall or something. So like my intermediate step. So just like here, I added an A term and a B term. I can add as many terms as I like. Some for N, F, N, I. Okay, that's the first step. And now I don't want to just jump all the way to the end, so I can add another wall with slits and another one. Let's start with 2. If we have 2, if I 1 and 2, that's 1. Then of course I can add as many walls as I want. And the nth n, 2, 1, f, n, 2, and 2, and 1. Okay. And then when we increase the capital N and the number of holes in each wall, in each one of these walls, I will eventually reach the fully continuous limit. Basically, what we have here is a simple description that says, let's look at all of the different possible paths the particle can go, sum them up, and then when we take the absolute value squared to get the actual probability, we'll have some interference pattern that will give us the full probability to take each path, or in the end just the probability of going from one point in 0 and ending in the second point in the time t, the interacting.
It's kind of like having a Stern-Gerlach or something like that, but with infinite degrees of freedom.
Yeah.
Instead of up and down, something like.
Yeah, a little bit. It's it will become a little bit more clear when we solve this. What it looks like. Okay. So now, skipping right ahead to the point at hand, we defined a propagator to assist us. For now, we'll call it K F Xi and T. The end location, the starting location, and the time that we take. 2 X F T F I T I. Okay. And we see that the probability to and this propagator we calculate by looking at the action. K of X F I T equal to, I'm just going to write D X E I divided by H bar S F X. Okay. Just an explanation on this this equation right here. S is the action. Just gonna write it down. F X I to X F dk 1/2. There is the kinetical energy term and the potential term. X. Right. Sorry, not X, this is T. T. And N is some normalization factor. I'm just going to write it and then I'm going to talk about the equation. Alright. So, we say, alright, the action, as we know from a classical mechanics, why it's so hot in here, god damn. The action, as we know from classical mechanics, it represents basically like a value for each path that the particle can take. Classically, we just try to minimize the action, and that will be our path. But in quantum, what we do is we say, okay, in each time, we move in time, t, x. In each time, a particle can move to a different location. Different location. And this movement will give us some value for the action. And this value for the action will determine a sort of phase component for this specific path. Each path has an equal probability according to the actions, and then the entire phase components, we can sum them up. This capital D of x means integrating over all the possible paths. Each phase of each path will interfere in the phase component that we receive from the action, and like that it will give us some sort of interference power that will eventually give us the probability function and the probability itself. Let's write it down. Let's also write down the definition of capital D. X equals n equals 1 and minus 1 n. Notice that it starts in 1 and in n minus 1 because x of 0 is our initial location, which we know, and x of n, capital N, is our final location, which we also know where it is. So there's no summation of it. Of course, we would like to take n goes to infinity if we can, and this delta t will be the difference between the time difference between each step. Another cool thing about this equation. Notice that we're dividing here by h bar, and in the classical limit, h bar is equal to 0. So every path that isn't the classical path will have some non-zero path here divided by 0, which will give us an infinite frequency of oscillation, and will just cancel out. So this equation, when you take it to the classical limit where h bar equals 0, will give us the classical solution if you fully analyze it. Right. It seems kind of daunting. How can you possibly integrate over every path? Each path will need to have some time integration over it. So let's do an example and see if we can solve this kind of thing. So with like every course, every example, every subject, start with a free particle. Because physicists can't solve anything complicated. Alright, free particle basically means V equals 0, and our action equal to 1 over half m x dot squared. Right? Propagator k t equal to n dx. e to the power of I divided by h bar, integration 0 tau t m squared divided by 2. Okay. Now, integrating over every possible continuous path is hard, so I'm just going to try to decompose this into like integrating over a singular point in time, discrete points in time. So, using this equation right here, you can open the integral. I see a problem. The normalization factor is written with the like kind of a squiggly n, and I cannot do squiggly. So I think I'm gonna change the letter just so you won't get confused between those two n's. I'm gonna call this A, just for simplicity. I'm sorry I can't do squiggles. N equals 1, x of n. E I m divided by 2 h bar. Oh, wait, I skipped them. Stop. Yeah. Let me just write here what we're doing to this to get it out of the continuous. The x there. We also need to do the same treatment with our time integral, because we're no longer continuous. So instead of dt, we have sum over n equals 0 n minus 1 of delta t. And finally, x dot equal x n to xn plus 1 minus xn divided by delta t. Okay, this is just derivative. Of course, it will be a summation in here because we have an integral. Okay, so yeah. Okay, so it seemed kind of daunting. Let's try to do it 1x at a time. There should be a d. 1x. Okay, integration over minus infinity to infinity. Again, this the question. In this question, we don't have any boundary condition for the particle. It can go anywhere it wants. So we have to integrate from minus infinity to infinity. dx1. dx2, dxn minus 1 times e I here to h bar delta t of x1 minus x0 squared plus x2 minus x1 squared plus xn minus xn minus 1. Again, reminding you that x0 is our starting point and xn is the end, is the finish line. Right. Now, so let's do this one part at a time. I1. Integration from minus infinity to infinity of dx1 e to the I m 2 bar delta t. Now the only terms that have x1 are the first two terms. Now, I'm just gonna focus on what's in the brackets, just to make it a bit clearer. So in the brackets, we have, after we open the squares, x1 squared minus 2 x1 x0 plus x0 squared plus x2 squared minus 2 x2 x1 plus x1 squared, which would be equal to 2 x1 minus x0 plus x2 divided by 2 plus x2 minus 0 squared divided by 2. Now this term has no xy in it, so we can take it outside. And we're left with basically with solving the integral minus infinity to infinity e to the power of I m h bar delta t of x1 should be a squared here, x1 minus x0 plus x2 divided by 2 squared. Dx1. I'm going to exchange u. If anyone has a better marker, speak now. Whoever holds your piece.
Just choose.
Oh,
Anything is only the part of the.
yeah, I didn't have time to go to the.
Where can you get free?
In the Moscow.
Oh,
The
okay.
head office. Alright, so I do this replacement. And notice that there is no added factor. The derivative on both sides is the same, it's 1. So this integral is just integral from minus infinity. Ooh, what a good marker. This is an integral from minus infinity to infinity of e to the power of I m h bar delta t square du, which is equal to square root of pi pi h bar delta t divided by I m. Yeah. Okay. So solution for I1. Unless I forgot the 2 here somewhere. I think I forgot the 2 here. Did I forget the 2 here? Oh, right. I'm keeping the half and then the half n times 2 for purpose. 2 pi I here t divided by m times the part we left out, which is this part, e to the I m 2 h bar delta t x2 minus x0 squared And notice that now our kappa propagator is equal to a times 0 to 1/2 2 pi I h bar delta t divided by m, the integration of dx2 to dx minus 1 of e im to h bar delta t 1/2 x2 minus x0 squared plus x2 x3 minus x2 squared plus xn minus 1 squared. All right, we solved one. We solved one integral. We can solve all the integrals, but I'll still do one more, like another step. Now for the second one, again we do one, we do two, and then we find the pattern. T of, now it's just these two terms that have x2 in them. Equals, just gonna write it real quick so we can go home. E I m h bar 2h bar delta t 3 divided by 2 x2 minus 1, so x0 minus 2/3 squared plus 1/3 x3 minus x0 squared. Right? Sorry, I'm just gonna skip right ahead to solving to the solution for this. Square root 2 over 3 2 pi I h bar delta t m e to the power of I m 2 h bar 3 delta t x3 minus x0 squared. Now we can start seeing a pattern. The x0 in the exponent keeps moving along from being x to x1, now being x to x2, and then being x to x3 later. And the denominator of this term keeps going down, the 1 divided by 2, 1 divided by 3, 1 divided by 4, etc., etc. And we have a shift in the normalization factor that equals to n divided by n plus 1 times this term right here. Right? Overall, if you take this conclusion and multiply them or reiterate them on all our integrals, we get propagator. We know we'll get that the propagator in would be similarly equal to square root of n plus 1, 2 pi I h bar delta t divided by m e I m divided by 2 h bar n plus 1 delta t x n plus 1 minus x0 squared. Just following the pattern that we saw after the first two integrals. So I'm multiplying I1, I2, I3, up to IN, we'll get, okay, can you see this? I'll write somewhere else. Okay, equal to E, square root of 1/2, 2/3, n minus 1, n, times square root of 2 pi I h bar delta t divided by n minus 1 e to the power of I m 2 h bar n delta t n minus x0 squared overall. Okay. Now n times the time steps is just the overall time. So here. And notice that these two cancel out. The 2 in the denominator here cancel out the 2 in the denominator here, and so on with the 3, and so on and so forth, and we'll just be left with 1/n. Right? And 1/n, and just reminding you what the a equals to, because I erased it. Yeah. A is equal to 1 divided by 2 h bar I pi delta t n by 2. Taking all of this into account and replacing the delta t here with t divided by n, we get that all this equals to square root m 2 pi I h t e to the I m to h bar t f minus I squared. Now, seems a bit weird. We have a function that, well, it has a phase that changes depending on our initial condition. The absolute probability of the particle to be found in any location in space is equal. If you start with a single location, xi, let's say xi is a constant, and xf is something that we can change. As we know from a free particle, the probability, which is k absolute value squared, will be equal in all space. That's the time. Let's take a small break because the next we're going to do another example which is a little bit more complicated. So that's like, I don't know how long we will be, 10 minutes? We'll have enough time to finish this, 10 minutes.
אפשרת רק את אלה שלא מבקר?
כן.
לא, שכן, אני שלא מבקר.
מה פה מתאפס גם? באמת?
אני גם לא יודע לפרוס פה.
למה זה פשוט?
לא, פשוט יותר קצר משמעותית. כן. קראתי לביטוי שהוא כזה, אבל לא הכל כמובן. אבל לקחתי את זה בריבוע, קיבלתי 4 איברים, ומתוכם
אני דיברתי בהרצאה, אבל ממש
לא ראית את האחרון, אבל בכלל שניים תקציב. ונשארים
לא
בסוף
סתם מסובר הסאמס.
עם כאלה שגם כמות ה-annihilation וה-acceleration שווים. ואז נשארים רק עם שלב.
אתה כל כך שמסובר הסאמס?
לא.
תתחיל מהביטוי הזה,
כן, בסדר.
תסתכל על זה בריבוע, ואז משם...
יונתן עשה את זה בקורס שלו במודפות העל, אבל אם היית בסדרת הרצאות. אז בערך בשיעור הראשון, כל הדברים שהיא עושה בשלוש הרצאות האחרונות, ניסה לדחוף בהרצאה.
כולל הרבה וויקים.
כן, כולל גם תכונות תרמודינמיות ומצובר עשה.
אבל בסדר, זה הגיוני כי זה קורס טובה.
כן.
יונתן, אתה לא לקחת פה גם K פריים. בשביל שלך.
לקחתי. בפנים?
כן. לא שעושים בריבוע לא צריך לעשות K פריים.
לא צריך.
עכשיו כאן זה יסתדר.
כי K פריים שיש לך שני פקטורים שאתה מסביר אותם אחד לשני ובכל אחד יסביר. אבל פה סכום פחות.
בחוץ למה?
כי אתה מפעיל את האופרטור הזה, אתה מפעיל אופרטור עבור קייס ספציפי. תכלס בסוף האין זה חיבור של כל ה... מה זה אין במקום? זה חיבור של כל החלקים. שתיים בית יותר.
כן, סיימת אותו כבר?
זה פה רוצה את האחרים. עשיתי שם מה שיכול.
Now we're gonna solve we're gonna solve the field integration question for an harmonic oscillator. So for a harmonic oscillator, the Lagrangian would be 1/2 m dot squared minus 1/2 m omega squared x squared. Now, a fun fact about this equation, since we need to calculate an integral of a quadratic of an exponent, we can only solve problems up to a second order, up to a quadratic equation in space and derivative. So basically, this is almost the most complicated question that we can possibly solve precisely without doing an approximation. The only way to make it more complicated is to add a constant and the first order part. So yeah, we almost finished with the entire subject with this question. So that's great. So let's write it down and see if we can and see how complicated it really is. So the K, this question, B, A, the normalization factor, D, X, E, I, M, 2H bar, dot, TI, TF, GT, dot squared minus omega squared x squared. Okay. Now we can start doing the entire process that we did earlier. It will be slightly more complicated, but most of all it will be way more messy. So let me suggest and introduce a new way to solve these problems. I'm basically going to say, okay, my particle can take any path it wants, but we know that a harmonic oscillator has some sort of classical solution. Basically, we know that it has a path that it follows classically, and we can assume that the real path that it will pass will be some sort of combination of the classical path plus some perturbation around it due to quantum fluctuation, blah blah blah. Right? So basically I can write that x of t equal xc of t plus xq of t, where xc is the classical solution that is known equals minus omega squared xc, right? And the quantum solution is the main thing that we would like to solve. We don't know it. But what we do know is that x in the initial state will be the classical solution, because we start with a singular point, we don't start with some perturbation. We can say the same thing in the final x. And at the beginning, in the end, the perturbation would be 0. Okay. Now, in addition, since the classical solution is fully deterministic, is a single path, you don't need to integrate over all possible paths for the classical solution. So dx, right here, dx is going to transform to dx of q, and overall, before I continue with the k, I'm actually going to rewrite the Lagrangian in the new form. So L will be equal to 1 over 2 m xc dot plus xq dot squared minus 1 over half m omega squared xc plus xq squared equals 1 over half m xc dot squared. Now I'm going to combine the classical terms, the quantum terms, and then we'll see, and then there will also be a mixture. Omega squared x squared plus 1 over half m q dot squared plus minus omega squared x q squared plus m xc dot x q dot minus omega squared xc x q. Bye bye. Okay, and I can write each terms as L classical q quantum plus L mixed. Great job. Instead of calculating one Lagrangian, I have to calculate using 3. Good. But these 3 will be much more manageable. Let's start with the very, very simplest one. The classical part of the Lagrangian, it goes out of the integral. Since we only integral over the quantum fluctuation, so one part is already solved, which is more than the 0 that we had before. And now let's look for a second at the mixed term. So the action of the mixed term equals m dt x dot c xq dot minus omega squared xc xq. Now I can integrate by parts the first term of this integral to be equal to m dt minus x dot c xq minus omega squared xc xq. Now notice that I neglected the boundary term, but the boundary term will take xq from ti to tf, and we know that xq in ti and tf is both 0. So the boundary term will immediately be 0. Right? And we can take outside the xq equals minus m equation dt x c 2 dots minus omega squared xc xq. Now from the classical solution we know this equals to 0. Oh, sorry, there's a plus. This equals to 0. Alright, so this is 2 out of 3. Immediately done. Immediately finish with 2 out of 3 a new Lagrangian. Now we're only left with S equals C, SK, SQ, and now K, I, T, equal to A, integration SQ, E to the I divided by H bar, S, C, X dot, plus I H bar, SQ, C dot, should be equal to A, the I divided by H bar, SC, capital D X, Q, E to the I divided by H bar, SQ. For now, I'm gonna swallow this exponent into the normalization factor, just for simplicity. Okay. So we noticed another interesting thing. Our propagation function of xf and xi would be equal to the exponent of the classical term times the propagation function of starting at 0 and ending at 0. Since we know in our decomposition to a classical and quantum part of the solution, the quantum fluctuation will start at 0 and end at 0. So instead of calculating the propagation function for 2 different locations, we just need the classical term times the propagation from 0 to 0. Now, K, 0, 0, T, equal A, D, Q, E, I, M, by H bar, from Ti, F, T, X dot Q squared, minus omega squared X, Q squared. I'm going to focus on this integral alone. So integration from dt of x dot squared minus omega q squared. This can be integrated by part, the first term, and we get integration dt x dot q x cube, x cube squared, and we're almost at the cool trick that we're going to get to. Q, sorry, there's omega squared here. Omega squared, x cube. Now I can look at this as a singular simple equation, or I can look at this as an equation with some operation in the middle, O, which we'll define as I think I missed a minus here, then a plus minus, or which we'll define as minus n divided by h bar, d squared, dt squared plus omega squared. And now our integral will be simplified even further. Dt x cube O hat xq. And now when we want to solve using operators, we have a few extra tricks to solve integral or complex functions, or complex problems. Just like when we have a complex differential equation, we use Fourier transform, we can do something very similar here. Fourier transform is something of a general method given a specific form, transforming stuff from real space to frequency space, but the same method can be done by translating into many different subspaces. Basically what I'm trying to say is I'm going to transform the xq into some subspace that will make the operator sort of disappear, make it much simpler, and then this will just be a quadratic integral. And by the way, this method will be the main method to solve this form of question of path integral. More specifically, usually it will be enough to just do a general Fourier transform. Just from the beginning, this is just a little bit extra steps. Okay, so I want to make this operator disappear, so I'll have to transform this into the eigenspace of this operator. So I'll need to find the eigenvalue and eigenvectors, an eigenfunction actually. So I want to write xq equal to sum n by n t. Right? Well, phi of n is defined by and integration dt of phi of n by m delta music m. Now I can do this on the board, but in almost every book that has some sort of a quadratic integral, the solution for the eigenstate of the problem will be given. So again, instead of just wasting like half an hour doing arithmetics on the board, I'm just going to give you the solution. The solution for this, finding this eigenstate will be Vn of t equals 2 over square root of 2 over capital T sinus n pi t t. Stop for a moment. Luckily for us, in this case, this just came out to be Fourier transform, which is the known solution for the harmonic oscillator. So we don't need to prove that this actually covers the entire space. Usually Fourier transform is enough. You don't need to do all the preamp that I did before. But if you do all this preamp, you also need to prove these two axioms. Right? This is general knowledge. And divided by h bar n pi t squared minus omega squared. Alright? So using this solution, the integral dt xq o xq will be simplified to sum over m and n.
If O is a Hermitian, it's guaranteed that its eigenvectors will create a Hilbert space, will generate a Hilbert space, right?
Yeah, I'm pretty sure.
Yeah, but
Yeah.
So that condition will be met, like for sure. If
Yeah.
O is Hermitian. You just have to.
Yeah, it's a note. I'm gonna add it as a note to the file that I upload because it's not really written here and I didn't think about it. Thank you.
But if it's not remission, you can always fix it in order to be remission with some weight function, right?
Yes.
Like the momentum operator, which the derivative is not remission, but you fixed it. It's the same, right?
Yeah. Well, do you remember where we see it? Like in what class? I think it's like it's not in this course.
No, it's not in this course.
I remember seeing it, but I don't remember where.
I think in the Memphis tree.
Probably in Memphis. Yeah. But just to make people feel a bit easier, you won't have this sort of complicated question in your homework or in a test. Okay? You don't have to think, oh, do I span over my entire Hilbert space? No. This is just a see if you know quantum course. We don't want you to start going back to basic mathematics. Yeah, very good catch though. Yeah. Okay, so the operator activating on phi, we know it's an, so integral dt, an, vn, vn, and vm equal to. Right. Now we have an integral over time over two autonormal function. So this would just be a delta of m and n. This entire thing would just be sum over n and the n, an absolute value squared. Oh my goodness. Oh my goodness. No. No. Going down here. We only need to fix the continuous integral, the dx q, to match our new eigen system, our new system. So we know that we can open this dxq, we equal apply n dxq n, and it would be directly proportional to an integral over an, just like normal Fourier transform. So we can replace it with the n over m of the an. Right, so k0, 0, t equals n e I by 2 n lambda n squared. All right. So we're just left with the multiplication of multiple Gaussian integral, which we know how to solve. The general solution for Gaussian integral of I divided by 2 lambda a absolute value squared would be equal to square root of 2 pi I divided by lambda. Right? Okay, 0, 0 equal to normalization factor 2 pi I times n minus 1 divided by 2 pi divide n goes from 1 to minus 1 divided by square root of lambda n. So Okay. Okay, fine. Now we just need to evaluate this part. We know that lambda n is some function n of omega, so we can write k of omega 0, 0, t, or more specifically, we know what's k 0, but there's no force. Right? Will be equal to square root of m divided by 2 pi I h bar t. And by using the ratio between k0, the known k0 and k omega, equal to pi is 1 n minus 1 of lambda n of omega divided by pi n minus 1 n 0 times, minus 1/2 or pi minus 1 n 1 of lambda n 0 divided by lambda n omega. Equals overall by n minus 1 n plus 1 n by t squared divided by n by t squared minus 1/2 equals minus 1 divided by 1 minus t now this multiplicative tool, this multiple product series, we know the solution of. Solution for this series, this product series, pi squared equal to the t sinus t. Overall, k omega 0, 0 t equal square root m omega 2 pi I sin right, and the overall k f to xi t equal the classical part, which we didn't calculate yet, times square root m omega 2 pi I h bar sinus omega t. So now we just need to calculate the classical action, which we already know, but let's do it anyway. Divided by 2, 0 for t, dt is I omega squared xc squared. One way to solve this is just to use the solution for the action, which a little bit long, so I'm not going to write down in the notebook. But another nicer solution is to do the same trick that we did before and integrate this by parts. So this integral SC will be equal, when integrating by part, m divided by 2 xc x c dot from 0 to t minus m divided by 2 0 to t dt xc dot xc plus omega squared xc squared. Now this term cancels out. The equation of motion, the classical equation of motion, and SC will just be equal to n divided by 2 xc t xc dot t minus xc of 0 xc dot 0. All right. Okay, I lied a little bit. We kind of need the equation of motion for the dot product, for the dots. xc of t is just xf. This one will be xi. And xc dot t would be equal xf minus xi cosinus omega capital T divided by sinus omega capital T. This is x dot of small t. Omega cosinus omega T minus I omega sinus omega t. Okay. Skipping a little bit ahead instead of like putting it in each term and doing the calculation by hand, I'm just gonna slot this in and hope that you believe me. I'll give you the final answer here. SC will be equal to omega divided by 2 xi squared plus xf squared times cosinus omega capital T divided by sinus omega capital T minus 2 xi xf divided by sin omega T. And overall, finally, k xf is I of t equal to square root omega divided by 2 pi I h bar sinus omega 6 omega t times e power of I n omega divided by 2 h bar x I squared plus f squared cosinus omega t divided by sinus omega t plus 2 minus 2 is I xf sinus omega. Okay. That's it. Good enough. Right on time. Any question before I leave? Thank you. Well,